Hi everyone, we are Shriya and Sinola from second year ECE, and this is our capstone project titled Smart Solar Tracking System using 8051 microcontroller. In this project, we aim to automatically rotate a solar panel using a microcontroller so it can follow the sunlight and improve the efficiency. We used Kale for coding and Proteus for simulation. We used 8051 microcontroller LDRs to detect sunlight and an ADC to convert analog light signals, a DC motor to rotate the panel, and LCD to display intensity. The logic is simple. Based on light intensity, the solar panel rotates left, right, or stays still. At the start, we initialize the LCD display to show the light intensity. We also enable interrupts to handle ADC data quickly.
We show the message light intensity and then update the values. Functions like LCD comment and LCD data are used to send comments and data to the LCD. When light falls on LDR, it sends an analog signal. ADC converts it to a digital value. It is done in multiply and divide functions.
We take the calculated value and split it into 3 digits to display on LCD. Each digit is converted to ASCII and printed on the LCD. This is the most important part. Based on light intensity, if the light intensity is greater than 66%, the panel will rotate right. If the light intensity is between 33% and 66%, the panel will hold in its original position. If the light intensity is less than 33%, the panel will rotate left. We use two control lines C2 and C3 to rotate the motor. This lets the panel track the sunlight and adjust automatically.
This loop keeps running throughout the day. Sense light, calculate intensity, display, rotate panel. This gives a real-time tracking of the sun.
We also show the intensity on LCD display. The code has 5 main parts: LCD initialization, enabling ADC interrupt, calculating light intensity, displaying result, and motor control.
We first initialize the LCD so it can show messages. The messages we display is we first initialize the LCD so it can show messages. LCD comment sends comment to the LCD. LCD data sends data to show characters. We use an external interrupt to read ADC data whenever new light input is available. This helps the microcontroller respond fast whenever there is a new ADC value.
We get the ADC value and convert it into percentage using light intensity percentage, which is equal to ADC value into 100 divided by 255. In code, we do this with multiply ADC value by 100, divide result by 255. Then we store the result in a variable called LDR. This holds the final light intensity in percentage. We then split the number into 3 digits, hundreds, tens, and units to show on the LCD.
Now we can display the percentage on the LCD. Each value is shown one by one, followed by a percent symbol. We rotate the panel based on the light percentage. This is done in the set motor function. Motor conditions. If intensity greater than 66%, it rotates right. Coil 2 on, coil 3 off. If intensity between 33% and 66%, it hold position both on. If intensity less than 33%, it rotates left. Coil 3 on, coil 2 off. This way the motor adjusts the panel automatically.
ADC reads the light value from LDR. Interrupt sends this value to microcontroller. The program calculates light intensity. LCD shows the value in percentage. Based on value, the motor rotates the panel left or right. This process runs continuously, so the panel always follows the sunlight.
Here you can see our Proteus simulation. The LDR gives light input. The ADC converts the analog signal to digital. The 8051 microcontroller reads it and decides which direction to rotate. The LCD shows the light intensity value in percent. High light on left side LDR, the motor rotates in one direction. Balanced light motor holds position. Low light on left side, motor rotates in opposite direction. This shows that our system automatically tracks the sun and improves efficiency.
Now let's conclude our project. Smart solar tracking system using 8051 microcontroller. We started this project with one main goal: to increase the efficiency of solar panels by making them automatically follow the direction of the sun. Normally, fixed solar panels don't always face the sun directly, so they don't get maximum sunlight all day. But in our system, the panel moves to track the sun, giving better energy output. We used LDR sensors to detect the light. LDRs give different values when sunlight changes. These values are converted from analog to digital using an ADC, that is analog to digital converter. We use the 8051 microcontroller to take the digital input, process it, and make decisions. The light intensity is calculated as a percentage and shown on a 16x2 LCD display. Then, based on the intensity value, if sunlight is more on one side, the panel rotates toward that side. If the light is equal, it stops. If the light is more on opposite side, it rotates back. This is done by controlling a desync motor using coil signals C2 and C3 from the microcontroller. By using interrupts, we made the system more responsive. It reacts quickly when new data comes in. It is a low cost solution for better solar energy usage. It shows how embedded systems, sensors, and motors can be combined for automation. It helps save energy and is a good example of using electronics for green technology.